For those of you who do not know me, my name is Ali Kujuri, and I'm from the Engineering Science Department. I'm one of the basically guys who, with others, put together this lecture series. And on the behalf of the department and the School of Science and Technology, let me thank you all for coming here. My thanks go also to Island Technology. No, I'm sorry, Keysight Technology, I'm sorry, for sponsoring this lecture series since 2006. Before I introduce our guest speaker for today, let me make 4 announcements. Number one, the pizza, as you know, will be here at 5:30, and I hope you enjoy it. Second, since we have a class starting at 6 o'clock, I would like to ask you to, those of you who will not be attending the next class, we leave the class, we leave the room by, let's say, 5 to 6 o'clock or so that we can clean up the room. Third, on the 21st, Wednesday 21st of this month, there is the Sustainability Day, which is going to be at the Student Center. And then you're all welcome to go there to attend there are a bunch of talks, very good talks, about sustainability and energy renewal, and so forth. And also there'll be some exhibitions you may want to, as engineers, to go and look, and then because there may be also some niches that for you that you may be interested in the energy and then the intersection of that. In fact, this is one of the reasons that, in fact, I invited Dr. Soto here. In fact, he's an expert. One of the reasons is that, first of all, he's an expert in the intersection of energy and environment. And then second, we are going to acknowledge the week of sustainability at the Sonoma State University, because the week of in fact, I think the 19th will be the Sonoma State University Sustainability Week. The fourth announcement is that on October the 15th, 2 weeks from now, we are going to have another interesting talk. The title is Innovation and Utility in Engineered Solutions, the CERENT Story. By the way, how many of you have heard CERENT? CERENT. Yeah, CERENT. Nope. How many of you have seen the CERENT when you come to the hallway here?
Oh, you
CERENT,
mean
yeah, CERENT, yeah. CERENT basically was a startup in late 1990s, and then they were basically had optical equipment. It was a startup, and then they started with optical equipment like wave division, multiplexing, and so on. And they did such a good job in bringing a bunch of things together and make small, equipment and so on, that Cisco bought them. Bought them for $7.2 billion. Imagine, and there were only like few engineers there, and you can imagine how much they enjoyed when when Cisco bought them. So this guy is, in fact, he was the director of marketing there. He's an electrical engineer, and then the first thing he did was that he employed himself and became an author and also consultant. For the lecture today, titled Estimations of Rural Electricity Demand, I have invited Dr. Soto, Daniel Soto, who is coming from the Environmental Studies and Planning. Dr. Daniel Soto is an assistant professor in the Department of Environmental Studies and Planning at Sonoma State University. Daniel teaches classes in the intersection of energy and the environment and how to use energy more efficiently. His research focuses on ways to improve energy access in developing world, and he earned his PhD in applied physics at Stanford University. He also has a Master of Science in Physics from San Francisco State University and a Bachelor of Science also in Electrical Engineering from Stanford University. Prior to his return to academia, Daniel worked as an engineer at 2 startup companies creating optical micromechanical devices and laser displays and optical communication. So let's just give him a hand there.
Thank you. So how many of you consider yourselves electrical engineers? How many of you consider yourselves computer scientists? And then what category did I miss? In between. Excellent category. Let's see. We gotta convince my computer to acknowledge the existence of this other monitor. Give me a second. All right. So first of all, I want to make the case, if you're interested in energy, if you're interested in climate change, electrical engineering, computer science, these are excellent fields to be in. We know how to make electricity reasonably cleanly with either solar panels, wind farms. We don't know how to store that. We don't know how to deal with fluctuating demand, fluctuating supply. Those are the sorts of things that you're learning how to deal with, right? And this is a time of incredible opportunity for folks. I just saw in the hallway somebody had done a project where they were trying to monitor washing machines, right? So that little sort of PIC-based project is the stepping stone to a much more sophisticated project where you're monitoring loads, you're trying to understand what's happening, and you're telling people and machines to do the most efficient thing possible to get the most of what they want, right? We want, what do we want? We want hot showers, we want cold soda, we want funny videos on YouTube, right? So how do we get as much of that with the least amounts of electricity, coal burned, carbon dioxide emitted into the atmosphere? And I'm here to try to convince you that this is something that you could tackle with the skill set that you're developing right now. So I'm trained in electrical engineering and physics, and then I've tried to pick up as much computer science because I really think that being able to take data and analyze it is sort of key to getting a handle on these projects, these problems. I'm also trying to understand, sort of without formal training, economics and some of the social aspects of how we use energy. Right? And so all of you like machines, I assume. You have some interest in making things. I'd like to convince you that you also need to have some interest in people, because almost all the machines you make are eventually going to be used by a person. So you have to think about how that person is going to use that thing, whether they'll like it, and sometimes whether they can afford it. So today, I want to talk to you about the work I do. I'm interested in the portion of the population that does not yet have access to electricity. How can we change that? About 20% of the world currently doesn't have that. What from my skill set can I use to understand that problem and improve it? Give me a second to pull out my notes. Right, so let me tell you about what we're going to talk about and sort of the outline. I'm going to give you a picture of what happens when you don't have electricity and what you have to do. I want to talk about some of the ways we have to expand access. I would love to see in my lifetime 100% of the world's citizens having access to electricity and clean cooking fuels. That might be ambitious, but I'd love to see it. Then I want to talk to you about a small place that's kind of an example, and not every place is the same. This place is unique. It's called Lake Sentani. It's in Indonesia, and I happen to have collaborators who are bringing in electricity. And so there's a natural experiment happening there where we have people who are basically neighbors, and some of them have access to electricity, some of them do not, and some of them will have access to electricity within the next couple of months. So we have an opportunity to observe what happens as people get access to electricity that will help us bring that electricity more cost effectively to other places in the future, right? So the basic question you might want to think about is how much electricity, if we were a community that didn't have electricity and we were going to buy solar panels and batteries, how many would we buy? And how would you estimate that given the fact that none of us own appliances that we might want once we had electricity? All right, so that's sort of the basic problem. So one of the things we call that is latent demand, right? If we don't have electricity, then we likely don't have refrigerators, we don't have certain things. After we connect electricity, how much new energy will we be demanding? And this is latent or hidden demand, right, that isn't revealed until you're actually connected to the grid. Right, so we're trying to estimate that to help with the planning process. So by way of introduction, I want to tell you that about 20% of the global population, sort of 1.2, 1.3 billion people, do not have the ability to do what we're doing right now. You should consider this amazing. The fact that we have lights means we have access to the most complex engineering feat of human history, right? The electrical grid. It is a large machine, possibly the largest machine we've ever built. We have access to that. 20% of the world doesn't. 40% cook every night without access to improved cooking technology. They don't use natural gas, they don't use electricity, they're usually using biomass fuels at some cost to their health, and they could be doing things more conveniently. So, and then there are agencies that are looking at this. This blue column right here is our sort of estimate, 1.2 billion. We think we're going to improve by the year 2030, but in some areas we'll actually get worse. There will be more people without electricity in some areas than others. And then as far as cooking fuels, these numbers are about twice what these numbers are. We think that this won't improve as much as the electricity will improve. So those are the numbers that I would love to see come down a lot in my lifetime. Now, this doesn't mean that people don't get the things they need, right? So what do we want from electricity? One key thing that people want is lighting, right? Anybody that's ever been camping understands that it's very different when the sun goes down. So we usually have portable lighting, we have maybe flame lighting, we have all of these sorts of technologies are used day in and day out by a significant fraction of the world. Another thing, and this has been in the last sort of decade, is cell phones. You find cell phones in places without electricity. That seems counterintuitive, but again, think about what the cell phone provides. The cell phone provides the ability for you to communicate with any person on the planet right now, right? That is an astonishing ability to think about. And again, even 30 years ago, you couldn't be off the grid and have that ability to communicate. Because of advances in electrical engineering, these cell phones are inexpensive today and can be purchased by large fractions of the world's population. So, improvements in things like solid-state electronics, lithium batteries have allowed us to get cell phones. Now, because they have batteries, you can take them to a place where there's electricity and then take that back to a place that doesn't have electricity and still use it, provided you're in radio distance of the cell phone towers. And then LEDs, another fairly recent advance. These are allowing electric light in new places. Before, if you wanted a flashlight, you had to have a relatively inefficient incandescent light bulb. So these two innovations mean that you can actually, tiny amounts of electricity, give people things they really want, like lighting and communication, in a way that's sort of cheaper, safer, and more convenient than other alternatives. And I'll talk about those alternatives. So let's say you live beyond the reach of the grid. What are your strategies you can do to get the services you need? You can take a battery and travel to a grid-connected location, right? That might be feasible for some folks. It's amazing. You can have communities that are 1 kilometer from the grid and have very little practical hope of being connected to that grid within the next couple of decades. You can use batteries to store energy. We see this. We see folks with car batteries or any sort of battery that will travel to a grid-connected location and then come back and sell that power. You can use fossil fuels for lighting. This is a very common strategy, to use kerosene or hurricane lamps in order to provide lighting. And then you can use fossil fuels for generators, right? You can actually buy, for maybe $100, a small generator, right, which is basically a gasoline engine. Kind of think about a large lawnmower engine connected to an electrical generator that can provide AC power with fuels, which are readily available anywhere in the world. Right? And so what do some of these strategies look like in practice? This is a bunch of folks who live close enough to a street light that they can go to that street light. That ends up being the study carrel for folks. And then they'll congregate, do their studying, and then go back home. These are dedicated students. I don't know how far I would have walked in order to be able to study at night. This is a battery on the back of a motorcycle. Sorry, it's a little dim. This is basically a car battery. When I took this photo, we were about probably 5 to 10 kilometers from a semi-grid connected location. And these folks would take that and then go back and then form a small sort of car charging business or allow people to use televisions based on that electricity. These are micro businesses. Now you can find these at airports, right? I'm gonna try to convince you. These behaviors are universal. There is nothing sort of strange about this stuff. You find, I've seen these at airports where basically you sort of put in your credit card, you stick your phone in a little thing, and it charges, and then you come back later. This is the exact same thing without the automation, right? So there's an entrepreneur behind the counter who will take your cell phone. He has an army of charging equipment. Will charge your phone and then give that back to you, right? So what ways can you make that easier, more efficient, more cost-effective? So these behaviors are universal. This is my in-laws. We are playing Scrabble during Hurricane Sandy. We're doing what people all over the world do when the lights go out, is they try to keep entertaining themselves, right? And so we were using flame lighting, which is dangerous. We were using LED lighting, and we were trying to stave off the boredom of being in the dark for several hours before we went to bed. And so I did all these same things. I put my laptop on my bike and rode my bike however many kilometers to the library that happened to still have electricity, downloaded videos for us to watch, charged up my laptop, sent out job applications for university professor positions, and then went back to a dark home, right? So, and we saw people in Manhattan wandering around looking for places to plug their phones in so that they could communicate, so that they could get lighting, so they could get all of these things that we sort of take for granted. All right, so now, some services we can get because they use tiny amounts of electricity that you can store in the batteries that we have. What about the things you can't do? There's some things that are harder to do. Refrigeration, right? This can extend the life of your food, decrease spoilage, right? That is a whole other order of magnitude of energy that you need and can't necessarily be supplied in the same way. You couldn't take that battery and run a refrigerator for very long. Air conditioning is in the same sort of order of magnitude. And then machines. So all of these things basically have one thing in common. You're running a motor. And once you start running a motor, you are in a new regime as far as the power usage and the energy usage. And so these things are not available, but everyone would like to have these things, right? So then the question is what is the most energy efficient, cost efficient way to bring these things to people that want them? I want to tell you that this is a business opportunity. Facebook is, first of all, Facebook has how many people online now? What is it? This came out in the news. It was 1 billion. Was it 2 billion? It's a significant fraction of the world is on Facebook. They still want to grow. So one of the things they're looking at is all of those people that aren't quite connected yet, right? So this is a business opportunity for them. Google, all of these folks. Imagine what happens when these folks can participate on the internet along with everyone else, right? What new things does that unlock when we can share in the human intellectual capacity of all those folks who are in some way cut off from the internet that we enjoy, right? And these folks are paying for kerosene, they're paying for cell phone airtime. These folks have purchasing power. All right, so now these strategies I told you before, though, they come at costs and risks, right? So kerosene lanterns, they have a fire risk. During Sandy, at least one of the deaths that we had in New York was because someone's candle fell over and started a fire. And then there were poisoning risks. Small children drink kerosene. They think it's water, just like here in the United States, right? You have to be careful with poisons. Wood fires, this is really the main risk, even though this isn't necessarily something you could solve with electricity, but it's important to understand. The particulates from wood fires, from cooking, cause lung damage. And this is a significant source of mortality in the developing world. And then travel to locations, right? This requires time, right? You could be doing something else with your time besides hiking to a place with electricity. So there's economies around this. This is what a tin lamp factory looks like. This is a factory that's creating lighting services for people, right? There are economies around this. These are some death estimates from smoke. So we expect by the year 2030 to have a large reduction in deaths from malaria. We expect to have a large reduction in deaths from tuberculosis. We expect to have a small increase in deaths from smoke from cooking, basically from starting fires. And we also expect to have a decrease in the number of people who are dying from HIV. Now what you see is that these 4 leading causes of mortality, within the next couple of decades, smoke will be one of the largest killers of people on the planet. So, and then again, this is not high quality light, right? When you think of an LED, that is an extraordinarily bright, I mean, we need to be in a time machine to be amazed by this, but, right, like this thing is amazing. It's this small, it's operating on this small battery, it's putting out enormous amounts of light, which you don't get to appreciate. All right, now I'm going to kill my phone on accident. Hold on, professor trying to learn how to use his phone. Danger. Right, this is an enormous amount of light that we can get from a very small piece of electronics. And that, again, that LED light, this picture would look very different versus, what's essentially maybe 4 or 5 times the brightness of a candle flame is what you can do with kerosene. All right, so now if you want to expand access, right, what are your strategies? One strategy you can pursue is grid extension, right? We have a grid. It works for 80% of the global population. Can we simply bring that out to these areas? Anybody think of a reason why that might be difficult? Cost. And so if you have a small, so I'm going to blow your mind. Some of these voltage transmission lines can be $10,000 or $100,000 per kilometer or more, right? So now you imagine that you're a small community at the end of one of those, and you're 10 kilometers away from the nearest node that you could connect to. Now you're talking about $1 million investment that needs to be paid for by the electricity bills of a fairly small community. That just doesn't pencil out, right? You wouldn't be able to pay for that investment. So that's one of the chief problems with grid extension. There's also, again, because of advances in batteries, because of advances in LEDs, because of advances in solar panels, for $10, $20, $30, $40 for affordable amounts, you can have a small power plant in your front yard. Now, that power plant will only be capable of powering an LED and perhaps charging a cell phone. So that's the limit of that. Again, these are two very, very key things that billions of people would gladly invest in, but they won't run your refrigerator, right? And so one thing that's interesting, and people are still trying to understand how to make this work, is there's sort of something in between. What if you have a community where you're dense enough, like everybody's close enough together that it makes sense to connect everyone to a central bunch of wires? But you're too far away from the coal plants to connect, right? You're too far away from the conventional generation, right? The big dams, the nuclear plants, the coal plants, the natural gas plants. Could you connect us, and then we could invest in photovoltaic panels, batteries, and create our own little self-sufficient system? That's the idea behind a microgrid. The difficulty, it's expensive. You have to pay for it before you use it. And so you need to get that investment right. So that's one of the things I'm interested in. I'm interested in places that want to look at microgrids, and I'm interested in thinking about how do we make that prediction of how much electricity we're going to need as accurately as possible. And what are the ways you can do that that will scale to billions of people? All right, can you do that in a very sort of easy way? I just talked about transmission lines to remote areas are expensive. And again, you might not have the infrastructure to put in a coal plant or a natural gas plant close to these folks, right? If you don't have roads, if you don't have rails, if you don't have all of those necessary things, you can't necessarily put electricity in. Renewable energy is relatively expensive. This is one thing. So for us here in the United States, we always talk about it needs to be cheaper than coal, which is fairly hard to do. Coal is a very established technology. We know how to dig it up really well. We can provide that electricity fairly cheaply. However, kerosene is expensive. In these areas, you're not competing with coal, you're competing with kerosene, and those economics solar can compete fairly well. And I mentioned earlier, solar lanterns can't provide for lots of the uses that people would like. They do provide some very important services, but again, you couldn't run a refrigerator. There are things that you could not do easily. One way to think about this, imagine you have a length of wire. Imagine you're trying to look at a community and you're trying to connect folks. Right? You have to buy that copper. It takes copper to connect people. And then it needs to be paid for by the amount of electricity that sort of flows over that wire every year. And these lines are meant to indicate the transmission cost. So how much more does it cost to make the electricity, to deliver the electricity over what it costs to make it, right? Because usually you need to make the electricity, but then you need to deliver it. So what it says is that this is basically going cheaper up this direction. So it's cheaper in the direction of shorter wires, and it's cheaper in the direction of more electricity, right? If you have somebody using a lot of electricity, you get to divide that copper cost by lots of people and lots of kilowatt hours. So if you, unfortunately, are in an area where your length of wire is very long and maybe your usage is likely to be low, you're in this expensive category where your community might not be able to afford it. So how do you define a microgrid? Ask anyone, they'll give you a slightly different definition. I think of a microgrid as anywhere from, say, 10 to 1,000 households with self-sufficient power production, right? And this is a model people are trying to pursue. I consulted for a company that's trying to do this, and it's tough. I won't lie. But so this is the sort of thing that I'm interested in, and we'll sort of talk about how we might think about planning for this for the next couple of slides. So that takes us to a place that we've been looking at. Actually, one of my students is in the room who's been looking at this place. He knows Lake Sentani. Indonesia overall is interesting. This is the fourth most populous country in the world. Overall, the electrification rate is 74%. Right, so 26% of the people don't have access to electricity. There's a real divide. 92% of the people that live in urban areas have it, but only 60% have it in rural areas. So really the difficulty is getting it out to these locations away from the cities. In all, that comes out to 60 million people without electricity. That's what, a fifth of the United States, something like that? We can show you what this looks like. I actually don't need the link. I think we can go straight there. This is Lake Sentani. Now what's fascinating is that here's an airport. These are some islands, and despite living a kilometer or two from the end of that airport runway, the folks on some of these islands don't have electricity. Right? So you can be extraordinarily close to a grid-connected area and still not have access to electricity. So how do you make that connection for those folks? This is what a small island, one of these small islands looks like. This is a challenge, right? So think of this as a design problem. You're engineers. How would you create enough electricity in this location for these people to use the services they want? I'm not saying this is an easy problem, but these folks want electricity. And question in the back of the room.
Ocean currents? Is that possible?
They're in a lake, so they won't have some of the tidal stuff. But so the most cost-effective game that people are trying is basically small solar photovoltaic systems. Now there are places like this in Washington State. You have very small islands. They just have an undersea cable. But again, if it costs $10,000 or $100,000 to string a wire on a pole, think about how much more it costs to put one under the ocean. Right? So that becomes much more expensive. So you can already sort of see this as a challenge. And again, this is a really dense island. There might not be a lot of room for solar panels. So this is challenging. Right? This is one of the aerial views of this location. And this is what some of the homes look like. They're on stilts. They're on the, so and a lot of people, these folks get their livelihood from fishing from the lake. And I think there's some tourism income as well. So that's what it looks like. So again,
So generator, batteries.
all of those things work. All of those things are being used. But they're sort of being used sort of in a patchwork, piecemeal kind of way. And so people are wondering, so my collaborators have been contracted by the Indonesian government to try new methods of delivery. And microgrids is one of the things that they're being asked to investigate and see if they can create a business model that's financially sustainable. That's the hardest thing. We all know that with donations, we can put in solar panels and inverters and batteries. We also know that those systems can fail within a couple of years if they're not financially sustainable. So again, we sort of asked this earlier, but what strategy would we take to bring access? What challenges would arise? Right, and the chief ones are usually geography, isolation, and then financial sustainability. So let's see here. All right, so that brings me into what am I working on, right? That was just about all background, right? So most of these new ways that we're trying to deliver energy are done with private capital, right? Governments are largely out of this. The people that are really trying to do new things are doing it with investment money, right? So, and in order for this to work, the investor actually has to get some return on their capital. Like it actually has to be profitable for people to do this. So people borrow money, right? And when you borrow money, you have to make a payment, right? So you have some sort of monthly payment that you have to pay back. And then basically, the electricity that you can charge, right? The tariffs you collect, the electricity bills have to cover that. That's the simple, sort of unavoidable financial mathematics that you have to make work. Now, ways that this can go wrong, if you get too ambitious and you bring too many panels, too many generators, too many whatever, the loan payment you have to make is going to exceed the amount of electricity you can actually sell, and your business will be doomed. If you don't get enough of these panels, you can have another problem where people want lots of electricity, you can't provide it, and you're going to have a lot of dissatisfaction in your customers, and a lot of possible unrest, right? Because they were promised a service that you can't actually deliver. Both of those things are bad for business, right? So again, the engineering problem, which is mixed with an economic problem, which is mixed with a social problem, is like trying to guess what does that need to be. So this is we had some data. One of my collaborators, when he was working on his PhD at Carnegie Mellon, we were looking at how generators were used. And so you could read off the spec sheet. So this was probably a sort of 100 kilowatt generator. The fuel consumption per kilowatt hour delivered is at its minimum when the generator is being used close to how it was designed, right? This is why you have gears in your car. Your car wants to run at a certain RPM. The generator is no different. If you're not running at that, you're using more fuel per hour than you would be at your most efficient point. When we looked at where the grid was actually being operated, it was being operated in this more inefficient space. The generator was too big. That means that it was costing more than it needed to put diesel into this generator, right? You had a mismatch, and that's damaging the economics for these things. And these generators, actually what they ended up doing was they said, okay, well, we're only going to run on weekends, or we're only going to run on nights, right? They weren't able to actually provide electricity all the time as we enjoy it. And I asked this question before. Given that there's no access, how much electricity do you provide? It's kind of a chicken and egg question, right? So some people have looked at things like this. Some economists at Berkeley have looked at how many appliances do people buy if their income is suddenly raised, right? They had some research they did. There was a program that was giving people money, and then they looked at, what appliances do people buy? One of my collaborators in his thesis, he said, well, once you know what appliances you have, can you figure out when those appliances are being used, how much power they take, what hours a day, and then create a profile, right, a time series graph of what the power demands are. And then you can start designing a system. And then Jay Taneja and some folks over at IBM in Nairobi are looking at comparing electrified villages to unelectrified villages and trying to understand, do villages that appear similar end up owning the same amount of appliances once they get connected, right? So you don't have a time machine, but maybe you have a village that looks like another village. It has been electrified a couple of years ago. How many people own TVs? How many people own radios? What does that look like? So we're trying to tackle this. And in some ways, we're going to use all of these things, but we're going to kind of ask, what happens? Do people buy appliances when they suddenly get an increase in electricity instead of income? If I suddenly bring electricity to you, what are you going to do? You can think of this as your 16th birthday. So on your 16th birthday, right, when you were 15 years old, you didn't drive very much, right? How much are you going to drive the day after you get your license or the day after you get your car, right? This is this latent idea, right? Those miles were waiting to happen, but they needed you to have the enabling technology, which is the license and the vehicle. And gas. You need all those things, right? So the company that we're collaborating with, we're Advancing Energy. I met the principal, Matt Basinger, while we were doing our postdocs. And then there's a university, Cenderawasih in Indonesia, we're collaborating to get this data. So they went around and they surveyed 1,184 households, asking questions about, how much energy do you use currently? If you had electricity, what would you do with it? Questions about, what does your home look like? Again, things that we think we might be able to use to understand what their electricity use would look like in the future. All right. So, and then what's great, again, I said this is a natural experiment where we're going to have electricity consumption that we'll be able to measure soon. Right? Some of these places are being electrified, so we can look at the before and after. This is a rare opportunity. And the households in this survey ranged from some folks were already connected to the grid, some folks had fossil fuel-based microgrids, and some folks are completely unconnected. Maybe they have generators, maybe they've got batteries, they're doing all sorts of other things. So there's two main methods, and this work is really just getting started, so we don't have all the results, but I'm going to show you what we've got so far. We've asked two questions, and we can't actually answer how accurately for probably another year. But we want to take a couple of guesses with the data we have now. So some ideas, how accurately could you predict electricity by taking an inventory of every appliance in every home? Go to every single home, right? Bring your clipboard, write down everything. You could probably do very well, but that's prohibitively expensive in terms of time. Could you just take a sample of those households and do the same thing? Right? Maybe that takes less time, and through the power of statistics, maybe you can still get a pretty accurate idea of what that consumption would look like. Where people want to go is, can I just take a satellite photo of a community and then pick out some things from that photo and understand what that community is going to be able to do? Right? Could I do that with machine learning? Could I have an image recognition software program that could look at a community and identify that quickly? Right? A couple of dollars worth of compute time on Amazon, you could figure out this problem. That's where you eventually would like to go. And the solar folks here in the United States have done that, right? When Solar City comes, they never go to your house, right? They're just clicking on a Google map trying to figure out whether or not you're a good candidate. So what do? We had students, just like you in Indonesia, survey households interested in electricity. They used tablet-based electronic surveys. This is nice. This allowed us to collect the data, upload it into the cloud immediately. Then we started to analyze that data, right? So the first thing you have to do is see if it's right. So predicting human behavior is difficult. Measuring humans is also difficult, right? So you have to clean all this stuff, validate it, see if it looks right. We're starting to do statistical analysis. We're starting to do visualization, right? Who has energy and where? Who has appliances and where are they? And then I like to talk about tools. So we use scientific computing tools in the Python language to do this stuff. They're really nice. It's amazing what you can do with this stuff for free. Yes, you have to invest some time, but it's incredibly powerful stuff. So I defined latent demand earlier. We want to estimate that demand for electricity that will occur once the electricity is made available. So we surveyed people's intention to acquire appliances. We asked them, you don't have this now, would you buy it once electricity? Yes, once you had electricity, yes or no? And we can also look at similar villages on the same lake that are already electrified and say, does the proportion of people with electricity, does the proportion of people with certain appliances look the same in that electrified area as the unelectrified areas? These are two methods we could use, and we can compare those. Right, and in the future we'll compare the actual electricity use to those methods. So we surveyed these houses. That's redundant. We add the appliances in each category. So now you can't be spared math. You can imagine that we put this stuff in a matrix. How many people like linear algebra? You should. So you could just think of this as a matrix, right? For every household I, you could say, put a 0 if they don't own appliance J, and then if they do own appliance J, you put a 1, right? Computers are really good at this. You do this. And then you want to figure out how many appliance J could be radios, it could be televisions, it could be fans, right? You can then sum over the I's, and that will tell you how many appliances in that area have that particular appliance, right? You can, if you know other things, you can take small subsets of that matrix and then figure things out, right? So one of the things we did was we said, okay, let's take the subset of that matrix based on these colors. I apologize, this legend is a little small. Grid electricity, 2 different kinds of microgrid electricity, and no electricity whatsoever. What you find is that even if you don't have electricity, 80% of the people or above have TVs, right? Again, things like lighting, things like communication, things like entertainment, these are such basic human desires that we get them whether or not we have electricity, and we find some way to get them. Now, other things, the examples are the rice cooker, the fridge, and the fan. They're much higher in areas that have grid connections, and you don't see them in areas that do not have grid connections, right? So the question is, once you get that grid connection, will these folks end up owning it at the same percentage or not, right? So that's the kind of question. And if you're going to install tens of thousands of dollars worth of stuff, you'd like to have a good handle on that. And then we can do the same sort of thing with another survey question about whether or not people say they're going to buy these things after they get electrified. You make another matrix. We can have a 0 be has appliance or does not want to purchase that appliance. And again, that's appliance J for household I. And then 1 say they don't have the appliance yet, but they would purchase it after the electrification. You can do the same thing. You can figure out the appliances of type J that would be purchased after electrification by summing over all the households. Now you know how many people would buy that. And now the total ownership after electrification is everybody that has it now plus everybody that says they were going to get it. That is one method of estimating. Is it accurate? Ask me in a year. I want a Tesla. I don't really want a Tesla. I want the ability to drive a Tesla without owning a Tesla. But, right, the chances of me actually doing that, very low. We can compare these. This is a graph that shows both of those. So this is based on the, how do I explain this graph? One of these is what people said they would do, and the other one is what people in similar communities actually have, right? So there's a mismatch between these two estimation methods, which doesn't surprise me. There are lots of things I would like, but that I actually can't afford, right? So if you tell me, what would you like to buy, I might overstate what I'm actually going to be able to purchase. So one of these provides an overestimate. Again, we'll get the data soon, well, soon on an academic time frame. Soon means 6 months, maybe a year. And then we can see, does the real number lie in the middle? Does it lie closer to the green? Are we going to get surprised and it's in the blue? This is what we're going for. So now what do similar villages mean? Again, you can turn this into a linear algebra problem. You can try to think about the different ways that villages could be similar, things like level of economic activity, proximity to areas of commerce. And you could, if you had 2 dimensions, you could imagine, well, if some villages are all clustered here, we could call that similar. And if other villages were clustered in some other area of the graph, maybe they would be similar. And you could ask questions about those villages. Right? So again, we compare those 2 things. So the future work would be to actually look at those village characteristics and see if we identify villages that are actually similar to each other and help us refine our predictions, right? When you think about the ideas of big data and stuff like that, you're actually trying to refine your predictions based on more relevant data, right? That is how the ads that pop up in front of your face whenever you're on the internet, right? Somebody has done a lot of linear algebra to try to get that ad in front of you as you click. We want to observe the appliance acquisition in these villages that are currently being electrified, see if it matches. And we'd also like to create probabilistic or stochastic models of energy use based on those appliance profiles and see if they match the actual use. Or are there things that we're not capturing, things that we don't understand about the way people are actually using that energy? And so, thank you, but I'm going to try to slip in a quick demo or two about some of these tools. So these take investment, but you can there's ways you can have the code, you could do maps, and then you can do things like, I want to see where people have rice cookers. And you can make little pie charts and figure out, okay, well, those folks seem to be around the perimeter of a lake. The green is folks that have it, and the red is those that don't on a percentage basis. And then you can see, well, wait a minute, maybe that's because those folks live in proximity to the grid, right? And these are tools you can make your own little visualizations with a little bit of investment in kind of learning things. You could ask the same thing about lighting. Now, when you look at lighting, all of these circles turn green because the vast majority of folks have access to lighting, even if they don't have access to electricity. And then we do a lot of these things. When I was in grad school, I had all these graphs, and I had no idea how I made them. I was like, where did this graph come from? There's tools now where you can actually have the code sitting right next to your graph, and you can go back and sort of communicate your results to somebody. And when they ask you, where did that graph come from? You could say, from this code right here. So these are the kinds of tools we use. This is fun stuff. This stuff actually runs in the browser. It's kind of got Python behind the browser. And you can do a lot with these things. It's really amazing how fast the tools are evolving. So that is definitely worth your time investment if that's something that you think you'd like to be able to do. If you can digest more data about how people are using the products that you're going to make, that's a powerful skill. If any of you are interested in learning more, you can reach me at sotod@Sonoma. And I think we got about 10 solid minutes for questions. Yes?
So when you're talking about the microgrids, they can be anywhere from 10 homes to 1,000 homes. Where do you find your best efficiencies? Closer to 10 or closer to 1,000? When you get bigger microgrids, do you seem to get cheaper per customer? Or do you lose efficiency?
You have to add other factors in. You have to add in the geography and topology. You have to add in how much electricity people are using. But most things are cheaper when you do more of them, right? The idea of the economy of scale, right? The more of something you produce, the better you get at it, the cheaper it becomes, right? We see that with solar panels. We see that with LEDs. But honestly, right now in the community, people are very skeptical about microgrid business models. They don't think it works. There are people who beg to differ. I was just at a conference a couple months ago, and a bunch of people on stage were like, we don't think microgrids are going to work. And then there was this guy we're installing microgrids in Nepal right now. We think they do work, right? So that's still a controversy about whether or not that works. And it will take time to see if they sustain. That's the most important thing. We have lots of examples of things that work for 1 year. We need things that are going to work for much longer.
Just a similar question. Why come they're not sustainable, microgrids usually? Is it because
The cost to revenue ratio, right? How much it costs to put that stuff in versus how much electricity people can actually buy and then use to pay back the investment. That's the chief problem with the financial sustainability. Yes?
So is that kind of using the microloan system and where they're for small, is that including people giving a discounted loan or no interest-free loans? Or is it, you know what I mean? Because there's sometimes Western countries will go into economically deprived areas and give low
Yes.
cost, or is this a pure business where we have banks and investment groups trying to figure out how to squeeze more money? That's.
I'm glad you brought that up. I stayed away from interest rates and all that kind of stuff, but it's an important thing. So one of the things that people are thinking about is, so if you borrow money, you have to rent that money, right? That's how your credit card works. I borrow $1,000, and then they charge me 1% per month to rent that money from them, right? And for a lot of businesses, when they're raising, that rent rate can be 10, 15% per year, right? So one thing you can do to make it cheaper is reduce the amount of interest rate, reduce the amount of rent you have to pay on the money you've borrowed. What are the ways you can do that? You can have governments provide that money. You can have people that aren't really as ambitious about getting all their money back as quickly as possible, loaning that money. So there's definitely people thinking about, and that's one of the things that actually drives what I do, is I'm trying to say, if we do things right, the risk of this particular microgrid failing is reduced. If that risk is reduced, people are willing to loan money at a lower interest rate, because usually the way things work is if it's a risky investment, you have to have a much higher possibility of making your money, you have to get a higher return, right? If I'm going to loan you $1,000 and I think I might lose it, I want $1,500 back. If I want to loan you $1,000 and I think you are super solid, maybe I only want $1,100 back because I don't expect to lose it. So that finance rate is an important part of this.
I just had another question. If you do install microgrids into these communities, don't you also have to train some people to maintain?
Oh, absolutely.
And is that going to take a couple years? So would that delay the implementation?
Not necessarily, but it would definitely threaten the sustainability of the whole thing if you don't have those people, right? If you don't have people that understand how to use these systems and how to maintain them, you can't expect them to keep functioning. But people all over the world learn quick, so you can train those folks. I've got fun photos of people just gathered around solar panels in countries all over the world. People are just, you go to solar panel school, you learn how to use these things, and you learn how to take care of them. Yes?
So are you collecting the data to find out what's going to happen, to predict what's going to happen when they get electricity, or are you collecting the data to predict what area you should bring the power?
Ooh, interesting. People are interested in both. I'm sort of just trying to approach it as a kind of statistical problem of can I predict this? But there are definitely people, the folks I talked about at IBM in Nairobi, they are trying to gather data from hundreds of villages all at once and then pick the best ones to go electrify, right? And it sounds sort of severe for if your village is not the best one to electrify, but in some ways it's kind of like what Tesla's doing with electric cars, right? They're choosing one car that they think they can sell, even though it's very expensive, and they're only selling it to the people they think they can, but with the hope of lowering the price over time and getting it into the hands of more people. So one thing people do is they take these microgrids and put them in communities that have a really high source of income, like maybe a mine or a fishing village or something like that, and they go to the places where they have the highest probability of success. And then the idea is, as you prove that business model, you can move into different communities that might be more financially difficult. In the back.
What are the failure mechanisms in these grids?
I've seen frogs. I've seen corrosion. I've seen melting. I've seen financial sort of instability. So they range from the technical to the economic to the social. I've seen grids where people try to demand to pay the same price for electricity that their relatives pay in the city. And so, but you can't deliver electricity in these areas for the same price as the city. You don't have the same economies and infrastructure. And I've seen things fail because the business owners were unable to educate the populace about this basic reality, right? There could have been other things. I don't know the whole story, but right? So that's a social problem in a way. There's the simple economic problems where I've seen that you just couldn't afford to keep buying the diesel that you needed to run the thing. And then there are all manner of mechanical failures, right? From interconnections to corrosion to, and again, in tropical environments, it's extremely demanding, right? You have levels of humidity, moisture intrusion, insect intrusion, the kind of stuff that the people designing inverters in Germany aren't thinking about, right?
Okay. I'd like to thank Dr. Soto for really interesting. And I'm glad that he really talked about the fact that if you want to make anything as a young engineer, to think about anything to make it work, you really need to design the right business model. Otherwise, you're not going to sustain. Thanks again.